Today we're going to talk about complex reactions. Complex reactions are reactions that involve complex ions, go figure. But complex reactions are pretty easy to figure out if you'll remember one very common rule. Generally, you can always know the number of ligands to attach to a metal cation if you double the charge on the cation. For instance, if you're trying to attach hydroxides to aluminum, if you have that hydroxide and you know the aluminum as an ion is a +3, then one of the choices will be to double the charge of the aluminum. So one of the choices is going to be 6 for the number of hydroxides, which it is here. Now notice when you have a +3 for aluminum and 6 hydroxides for a total of -6, then our overall charge is going to be a -3. And that's the main thing that AP is looking for. They'll actually take kind of a wide range of answers as long as your charge matches your formula. Because honestly, in real life, how many complex ions attach or ligands attach onto those metals depends on concentration, things like that. So, but the easiest thing to do is just to double the charge. Take, for instance, ammonia attaching to silver. Silver's charge is a +1, so we can count on doubling that charge to 2, and sure enough, that's how many ammonia or amine ligands attach. Same thing for the cyano ligands that attach. All of these +2s down here, zinc, the copper, cadmium, double the charge, so we end up with 4 attached to those metals. And finally, one of the favorites of the AP world, iron with a thiocyanate, one of their choices is just to attach 1 to it. And you'll see this in a lot of labs, so that's probably the most common way you'll see it on their stuff, but they accept double the charge as well, 6 of them. And that is what happens sometimes, especially when it's formed as an anion. So with that in mind, look at some choices here. It says we've got concentrated ammonia added to a solution of copper 2 nitrate. I can't emphasize this enough. If you see a classic ligand, and the reason I made you write the formulas and name those names, so many of them, is that it gets in your mind water, ammonium, hydroxide, those kind of things. Classic ligand plus a transition metal. In this case, we're going to count all of the metals in that sea of unknown charge up to the staircase as being cousins to the transition metals. So classic ligand plus a transition metal. That's going to be your clue that you're dealing with a complex reaction. Another is this word concentrated. Concentrated ammonia, so there's the classic ligand, and there's your transition metal, copper. And what virtually always happens is that whatever's with that transition metal is going to drop out. And that part you really need to realize is going to happen, or it's going to make it much more difficult to do these reactions. Notice that it's a ligand, notice it's a transition metal, drop out what's with it. So we've got NH3, we're adding the copper 2+, and remember, double the charge means we're going to attach 4 NH3s onto this. And make sure we remember to keep track of the charge, because the charge is still going to be a 2+. Now occasionally you'll see AP not put brackets around their simpler complex ions, if that makes sense, but I always do. I don't like to see any kind of coordination sphere without brackets around it. Now, in order to balance this, make sure you put in that 4 with the ammonia so that you'll have it balanced. Balance, 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 balance. Okay, the next one, and this next one we're adding sodium hydroxide to a solution that's still hydroxide, aluminum hydroxide. So when you have this type of situation, you're going to get more hydroxide added onto this particular compound. So when I react this, the sodium hydroxide, and keep in mind that the sodium is going to drop out. I'm just going to go ahead and drop that out now because it's not going to show up anyway. So the sodium hydroxide is added to aluminum hydroxide in solution. Now, normally when we write that aluminum hydroxide, we will in complex reactions, we will often end up not splitting it. It wouldn't split anyway because it says it's a solution of aluminum hydroxide, but it's going to have to be a really weak solution because we're going to add more base to that, and what we're going to end up with then is our double the charge. Aluminum's a +3, so we'll end up with that OH6. And remember, keeping track of the charge, 3+ for aluminum, 6 negatives for the hydroxide. So overall, this is going to be a 3-. Don't forget to add on the hydroxides. Now, I don't think anybody would count this wrong. I know I would not. If you, since it said solution, went ahead and wrote it like this. Now, I'll erase this in a minute because I'm kind of oozing down into the next problem. But let's say you've got this situation and you go ahead and you split this and you write it and you complete it. I don't think anybody would really count that wrong, but I really see it more often this way with complex reactions not splitting in water. I know that's weird, but true. Okay, so let's look at the last one. The last example has 5 drops of sodium thiocyanate added to a solution of iron 3 chloride. So again, this is one of AP's very favorite reactions. So sodium's going to drop out. As soon as we see this thiocyanate ligand added to a transition metal, just drop the things out that aren't going to be involved. So we've got the thiocyanate reacting with the iron 3+, and you can do it with the FeSCN 2+, but I personally like to just keep it double the charge all the time. So I'm going to write it like this, FeSCN 6. And if we do that, our 3+ and our 6- we're going to be here with that for the charge with a 3-. And of course, we need 6 of our thiocyanates to react with it. So you can see that if you try to do this as a double replacement reaction, you're not going to be able to figure out what it is. Please treat this as finding a ligand, finding the transition metal that's involved, Xing out the other things that are with it, and just go with the ligand and transition metal for that particular reaction.